loop-the-loop problem. So I was actually doing this problem for something else, and I was like, let me just check my answer real quick. And I didn't see the solution, so I was like, hey, that means I have to make the solution. So let's do this problem. Let me describe the problem. So you have a car, let's say it's a car rolling down a track, and then it wants to go over this loop. So it's not powered, it's just rolling. And so the question is, if that has a radius of r, how high above the ground do you have to release the car so it makes it around the track? Now, of course, the first option would be, hey, well, energy is conserved, so if I release it from right here, it's going to make it up there. And it will make it up there. But what will happen is it'll go down here, and then it'll go, bloop, fall. Okay, but we wanted to make it around the loop. Now, I'm going to erase this because it's a little bit too big, and we'll solve the problem the right way. I'm going to redraw it in a smaller way. Okay. Okay, so here's my loop. Like that. Is that good? And then there's my car. I'm going to start that at position 1 with velocity 1 equals 0. And then down here, it's going to be right there. And at that point, it cannot have a velocity of 0 because it won't move in a circle. So let's go ahead and find the minimum velocity to move in a circle, in a vertical circle, and stay on the track. So here's my loop. Here's my mass, my car, and there's the center of the circle. Now, as it rolls around, there could be two forces acting on it. I have the downward gravitational force, mg, and then I have the normal force, N. So let's just go ahead and write Newton's second law at that instant where it's moving with some velocity. I'll call that v2. In the y direction, F net y, I have minus N, the normal force pushes down the track, pushes down on it, minus mg, and that's going to be equal to the mass times the acceleration. Now, the object is moving in a circle. So remember that the circular acceleration, we call that centripetal acceleration, is negative v squared over r. I'm sorry, it's v squared over r, but it's towards the center of the circle, so it's going to be pointing down. So I can write this as m, negative m, v squared over r. Now, we can solve this for n. I'm going to solve this for n. I multiply everything by a negative sign. N is going to be equal to m v squared over r minus mg. Right? Okay, now, notice that if the velocity is too slow, if this is a small number, then this is going to be more negative than that, and the normal force is actually pushing up in order to make it move in a circle. But we don't want that. We want a normal track where the normal force pushes down or not at all. So the minimum velocity is where the normal force is equal to 0. If that's the case, then I get mv squared over r equals mg. And so the minimum velocity, actually I don't need the minimum velocity. The minimum velocity squared is going to be equal to g times r. That's it. Okay, so v2, the minimum velocity is going to be v2 squared is g times r. And let's just, oh, you can't even see that. v2 is g times r, v2 squared. Okay, let's just check the units right here. This is in meters per second squared times meters. I get meters squared per second squared, which is the unit for velocity, so that's good. Okay. So now I know how fast that thing has to go. I can go back over here. So let's use the work energy principle, and I'm going to pick the system of the mass, the car, is going to be the car plus the Earth. And if I have the Earth in my system, then I can include a gravitational potential energy. Now, you may think that's a silly step, and I agree it's kind of silly, but it's important to do it the right way. If I have to do that, okay. So now I can say work as the change in energy, which is going to be the change in kinetic energy of the car. We'll assume the Earth doesn't move, which is a pretty good assumption. Work, change in kinetic energy plus the change in potential energy. And so the kinetic energy is 1/2 mv squared. The potential energy is mgy. Now, I'm using mgy, and that's fine. I have a change in potentials. It doesn't really matter what the value of y is because it's a change in potential. I need to pick some place where the potential is 0 and just set it there. Of course, the obvious thing is to pick y 0 right down there. So now I can pick this position and that position as my 2 points. As the car goes along that, we have 2 forces acting on it. The gravitational force, but we do not do work done by gravitational force because it's part of our system. And then we have a normal force. The normal force also doesn't do work because it's always perpendicular to the direction of motion. So the work is F delta R cosine theta. Cosine theta is 0. So it doesn't do any work. So I have no work done. So I can say 0 is K2 minus K1 plus U2 minus U1. Okay, so what's the kinetic energy up here at point 2? That's fine. 1/2 mv2 squared minus the initial kinetic energy, which is 0, that's a 2, plus the potential energy at point 2 right there is going to be its height, which is mg2r, right? Because if that's a radius r, that's 2r. And then I have minus the initial potential energy, mgh. I want to solve for h. Okay, so let's put in, am I running out of room? I can do it. 0 is 1/2 m, v squared is gr, plus mg2r minus mgh. So let's move this to the other side, and I can divide by the mass, and I can divide by g. So I get h equals 1/2 r plus 2r. That's right, 1/2 r, 2r. So it's 2.5 r. So this is going to be equal to 2.5 r. So I can't release it right here at the height. I have to release it a little bit higher, 2.5 times the radius of that. And that's it. That's the answer. Okay, now let's do one more thing because it does come up. So imagine that I release it from some height, any height. What is the g-force at the top of the circle? Okay, in this case, what would the g-force be and what is the g-force? Okay, so we've got a bunch of stuff to do. I'm trying to decide. Yeah, I'm going to use that equation again, but that's fine. We'll just rederive it. So what is the g-force? So the g-force is the normal force, right? Because humans don't experience the force from the gravitational force. If I'm just standing here, I feel 1g, right? That's what it feels like, and that's because the normal force pushes up on me with the same value as the gravitational force. If the elevator accelerates up, gravity doesn't change, but I feel heavier, and so as the normal force increases, the g-force increases too. So I'm trying to find the value of the normal force in g's. So let's say I release it from initial height, let's call it y1, and I want to find the normal force. So the first thing I need to do is to find the speed. Okay, so again, doing the work energy, I get 0 is the final kinetic energy, 1/2 m v2 squared minus 1/2 m v1 squared plus mg y2 minus mg y1. Okay, that's 0, right? I'm going to release it from rest. Y1 is something and Y2 is 2R. So I get 0 is 1/2 m v2 squared plus mg2r minus mgy1. Now what I want to find, the normal force, if I go back over here, remember I had N equals mv squared over r minus mg. That's what we got from before from looking at the forces on that object. So I need v squared at the top. So let's just solve this for v2 squared. So I have 1/2 m v2 squared is going to be equal to mgy1 minus mg2r. And now you could combine those two together. It wouldn't be a bad idea. So let's do that. That's going to be mg times y1 minus 2r. Now I can divide by the mass. I can multiply by 2 because I want v squared. I don't even need v. I need v squared. So I get v2 squared is going to be 2g y1 minus 2r. Now, if I put that in there, I want to find the normal force in g's, so you can factor out the mass, and that's fine. So I get N equals m. V squared is this, so it's going to be 2g y1 minus 2r over r minus g. And that's my normal force. Okay, I should have got my calculator out to find that. And then if I factor out the g too, I get the whole thing. N equals mg times 2 y1 minus 2r over r minus 1. And let's just check. So that's going to be this is going to be my units of g's. And this is units of distance over distance, so it doesn't have units, minus 1 doesn't have units, so everything works out okay. So you can plug in your initial height and find out that force. If you plug in the height of 2.5 right here, 2.5r minus r, I get 0.5. I multiply that by 2, I get 1, so I get 0. So you'd be weightless at the top at the perfect height. As you go faster, as this increases, then your g-force increases, and there you go. So again, I just did the problem because I hadn't seen the solution, but I hope you enjoyed that. The end, I don't have anything else to say.